So last time we talked about finding the pH of a weak acid using an ice table and the equilibrium constant, and then finding the concentrations of the species equilibrium, one of the products being hydronium, H3O+, and from that we can calculate pH. pH is the negative log of hydronium. We also did this for weak bases, where we found, again, the ice table for the equilibrium reaction, and at the end of the reaction we have the equilibrium concentrations of all species, one of those products being hydroxide OH-, which we can use to find POH, and then subtract from 14 to find pH. Then we talked about going between the Kas and Kbs, the conjugate acid bases. We're going to use that in a little bit, but first we're going to talk about what to do if there is more than one hydrogen ion present on the acid. So we talked about this very briefly back in chapter 4 about polyprotic acids. So all of the acids, the weak acids we've been dealing with up to this point were all monoprotic, meaning they had just one acidic hydrogen available to be donated in the reaction. However, we have several acids that actually have more than one. So this is carbonic acid. Carbonic acid is what we call diprotic because there are two hydrogens present that can both be donated. Now, we also learned back in chapter 4 that when this happens, these hydrogens come off one at a time. They're ionized in separate reactions. And we also learned that those reactions get weaker and weaker as they continue to lose hydrogens. In other words, the equilibrium constant is going to go down. These reactions are going to happen less to the product side and stay more on the reactant side, which means that each of these reactions is going to have its own equilibrium constant, its own Ka value. And the Ka1 versus 2 versus 3, they're going to get smaller and smaller because these reactions are going to happen less and less. So in the case of carbonic acid, we have the first reaction of the first hydrogen coming off to leave us with hydronium and carbonic acid, and hydrogen carbonate. The second reaction, that hydrogen carbonate loses its hydrogen to go all the way down to the carbonate ion. Now, when we're finding the pH of an acid, which species are we really interested in here? Which one of these is going to tell us anything about the pH? H3O. Now notice H3O is produced in both reactions. So if we're going to find the pH of this, we need to do an ice table for both of them to find out how much hydronium was produced in both reactions in order to determine. Now, at the end of the first reaction, we're going to have equilibrium concentrations of H3O and hydrogen carbonate. So our equilibrium concentration of hydrogen carbonate at the end of the first reaction is what goes in as the initial concentration of hydrogen carbonate at the start of the second reaction. So same as we did for weak acids that were monoprotic, you just do it 2 or more times. So just do it once for every hydrogen. So here are some tables. This is on page 750 for those Ka values for some polyprotic acids. Now, sulfuric acid is different from all the rest of these because sulfuric acid is the only polyprotic acid we have that is also a strong acid. So by definition, strong acids ionize completely and therefore don't need ice tables because they're not at equilibrium. They go 100%. But as we learned in chapter 4, only the first ionization or the first hydrogen coming off of sulfuric acid happens completely. So that's why we write Ka very large. In other words, you don't need an ice table. You can just assume 100% to the right, 100% to the products. But the product does not go all the way to sulfate. It just goes to hydrogen sulfate. The second Ka, so Ka2, this is when the second hydrogen comes off from the hydrogen sulfate to the sulfate ion. That is 1.3 times 10 to the negative 2, which is still a pretty big Ka compared to if you look at these other Ka2s that are much, much smaller, or if you look at just the table of weak acids that we had last time when we were looking at, like, for acetic acid, it was 10 to the negative 5th. So 10 to the negative 2 is still a pretty big Ka. So this is going to be a very strong acid and have a big impact on the pH. We have oxalic acid, sulfurous acid. So sulfurous acid is based on the sulfite ion, not the sulfate ion. Ascorbic acid, also known as vitamin C. And then we also have things that have more than 2 protons. For example, phosphoric acid is triprotic, meaning it has 3. So therefore, it's going to have 3 Ks. So this is Ka1, the first, Ka2, the second ionization, and then this one here is Ka3, the third ionization, because we have 3 hydrogens that can be donated from the phosphoric acid. And as you can see, each ionization is getting weaker and weaker and weaker to the point where that third ionization, it happens a very, very small amount. All right. Let's try this out. Oxalic acid, which is diprotic, is a poisonous substance used mainly as a bleaching agent. Calculate the concentration of all species present at equilibrium in a 0.1 molar solution to 25 degrees Celsius. And they've gone ahead and pulled from those tables those Ka1 values and Ka2 values. And they're written out, their equilibrium reactions for you. So what we're going to have to do here is do 2 ice tables. Give you a chance to write that down before I pull up a slide. So first, we're just going to focus on the first reaction here. This is also on page 751. Let me pull up some space. Just a blank, completely blank. So we have oxalic acid H2C2O4. And on the product side, we have the hydronium ion and then hydrogen oxalate. C2O4. Negative. Sorry. So what column here are we going to ignore? H2O. Go. We're going to ignore the water column because it's liquid, so it doesn't affect the equilibrium. What's our initial concentration in this problem of the oxalic acid, H2C2O4? 0.10, good. We were 0.10 molar. And initially, we have nothing of the other two. On our C row, our change row, how much is the oxalic acid going to change by? Minus X. So each of these is going to be plus X, 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 0.10 molar minus X. Next, we write our equilibrium expression. So equilibrium expression is the concentration of the products over the concentration of the reactants. So my products are hydronium, hydrogen oxalate, and on the bottom, my reactant is the oxalic acid, C2O4. Now this is going to be my first ionization, so this is going to be Ka1. So we were told, or we could look it up in the table, the Ka1 value for oxalic acid is 6.5 times 10 to the negative 2, which is fairly large. And on the top, we're going to have x times x, or x squared. And on the bottom, we're going to have 0.10 minus x. Now what? Quadratic formula. Now, normally I say you can go ahead and make the assumption that x is small, which means you can ignore this minus x on the bottom. But I'll go ahead and tell you with a Ka value that big, you're going to end up with larger than 5% ionization. In fact, for this problem, we ended up with 81% ionization. So that's definitely a bad assumption. So we're going to do the quadratic. For the sake of time today, I'm just going to go ahead and tell you what the answer is according to the quadratic, just to save us some time. So the answer according to the quadratic is x is equal to 0.054 molar. So now we're going to plug that in to our table up here, and for all of our x's. So our original oxalic acid is now going to be down to 0.046. So that is our first ice table. All right, second ice table now. We're going to have the hydrogen oxalate ionized. Same thing as ionizing with water at equilibrium with the hydronium ion. And now we're just going all the way down to oxalate ion. And ignoring water. So at the start of the second ionization, what is our concentration here of hydrogen oxalate? Good. What is our concentration of hydronium? .054, right here. We had 0.054 molar hydronium at the end of the first ionization, so going into the second ionization, that is our starting concentration. And what is our starting concentration of the oxalate ion? 0. That's starting at 0. So, yes? This one, right here? Not 0.054, because it's 0.10 molar minus X. So 0.10 minus 0.054 is 0.046. Because that's for the oxalic acid. Oxalic acid isn't anywhere in this equation. H2C2O4 isn't in the second ionization. Yes. Yeah. The hydrogen oxalate here is ending up here. That's where it's not going. Now instead of using x, because we've already used x as a variable, I'm going to use a different variable, so I'll just use y minus y plus y plus y. Y 0.054 plus y and 0.054 minus y. My y's curvy so they don't look like 4s. There. Now we're going to have Ka2 for our second ionization. Is going to be the hydronium, the oxalate ion, C2O4 2 minus, and on the bottom, the hydrogen oxalate. You can look at the table, or I had it in the setup. The Ka2 value for oxalic acid is 6.1 times 10 to the negative fifth. Top here, we're going to have y times 0.054 minus y. Plus y, you're right. Plus y. And on the bottom, we're going to have the 0.054 minus y. Now you can do quadratic, certainly, but at this point in time, our Ka value is small enough we can get away with making the assumption that our variable y is going to be small, and we'll end up with less than 5% ionization. So if we assume that y is small, then what variables are we ignoring here? All of the y's? Which ones are we going to ignore? We've got y in 3 places. Which ones are we going to ignore? We're going to ignore the one in the denominator. Where else? In the parentheses. So we're ignoring when it's being added or subtracted, because adding or subtracting a small number has very little impact on the final answer. But we cannot ignore the one where it's being multiplied, because multiplying by a very small number does have a big impact. So when we do that, what happens to my 0.054s? They cancel. I have 0.054 on the top and the bottom, so they cancel. And I'm just left with y is equal to what? Good. 10 to the negative fifth is my y. See how nice that assumption is when we get to make it? It's so much easier. So we can plug that in for our y's in the equation, or in our ice table here, here, and here. Now, our assumption was that y was so small that adding or subtracting it doesn't make much of a difference. And sure enough, if you go and plug into your calculator for this line right here, 0.054 minus 0.054 minus that 6.1 times 10 to the negative fifth, you'll get 0.053939, which once you round to the sig figs that we have, is still 0.054. So this answer here is still going to be about 0.054. Same thing with the hydronium ion concentration. When we add it, it's still going to be approximately still 0.054. But our concentration of oxalate ion, that is now going to be y, which is 6.1 times 10 to the negative fifth. So the question was, what is the concentrations of all species at equilibrium? So our concentration of our oxalic acid is the 0.046, and then our concentration of the hydrogen oxalate is 0.054. hydronium 0.054, and the oxalate 6.1 times 10 to the negative fifth. So there are our 4 answers. If you wanted at this point to find the pH, what would we do? Good. Negative log of the hydronium ion concentration, so negative log of that 0.054. Yeah. 0.046, 0.044, 0.054, and the 6.1 times 10 to the negative fifth. And then they went ahead and checked the percent ionizations just to make sure that it was less than 5%, meaning that assuming Y is small was a good assumption. They also have the math there for if you assumed X was small, what would you get as the percent ionization? And they got 81%. That's why they went back into the quadratic. Good. All right. So again, polyatomic ions, exactly the same thing as any other weak acids. Or polyatomic acids, polyprotic acids. Polyprotic acid is the same thing as any other weak acid. You just have to do the ice table more than once. And your equilibrium concentrations at the end of the first ionization are what go into and populate the initial concentration in the second column, the second ice table. All right, next section. Molecular structure and acid strength. This is looking at the structure of the molecules and using that to predict relative strengths of acids and explain once and for all why HF is a weak acid even though it's in the same family as all those strong acid, hydrochloric, hydroidic, hydrobromic. Why is HF still a weak acid? So hydrohalic. The word halic means dealing with the halides. What are the halides? Also known as halogens. Group 7, good. So that's the fluorine, chlorine, bromine. So hydrohalic acids are HF, HCl, HBr, those ones. And then we'll talk about the oxo acids. So this is like the sulfuric acid, carbonic acid, all of those based on the polyatomic ions, and then carboxylic acids. So that's going to be things like the acetic acid, and we'll talk about how the structure and why did we start rewriting the acetic acid with the hydrogen at the end instead of in the front like we did back in chapter 2. So first of all, hydrohalic acids. So it's a halogen, which we're just going to write it here as X, with a hydrogen in front. So this X could be fluorine, it could be chlorine, it could be bromine, it's just one of the halogens. So the ionization of this, the hydrogen ion comes off and you're left with the hydrogen plus ion and the halogen minus ion. So in order for this to break apart, there has to be a relatively weak bond in between the hydrogen and the halogen there. The weaker that bond, the more easily it will lose the hydrogen. The more easily it loses the hydrogen, the stronger the acid, because acid strength is defined as how much hydrogen ion it releases. And in fact, for a strong acid, it has to release close to 100% of its hydrogen ions, whereas weak acids only do to a certain amount and go to equilibrium. So the weaker the bond between them, the stronger the acid. Now, this bond is what, molecular or ionic? It's ionic. Sorry, not ionic. Ionic would be a metal and a nonmetal. Therefore it's molecular. 50-50, it's molecular. So it's molecular. In fact, it's polar molecular. So we're looking back at chapter 8 and those electronegativity values. Remember, electronegativity increases as you go across a row and up a family. What is the most electronegative element that we have, therefore? Fluorine. Fluorine is the most electronegative element that we have. So electronegativity, we learned in chapter 8, is how strongly it pulls electrons towards itself, the more it wants to pull things towards itself. So that's what causes things to become polar. In the case of a hydrohalide here, the electrons are going to get pulled in the direction of the halogen. So if this is HF, it gets pulled towards the fluorine. Fluorine becomes partially negative, and the hydrogen becomes partially positive. Now, when this happens in something like HF, the fluorine ends up being negative, and the hydrogen ends up being positive. If we compare between HF and the other halogens, so, for example, chlorine, bromine, and iodide, this still happens but not as strongly because chlorine, bromine, and iodide are not quite as electronegative as the fluorine is. Therefore, the degree of polarity is going to be less for them. If the degree of polarity is less, then those partial charges is smaller. Now, those partial charges makes it similar to an ionic compound. Opposites attract. If you have a large charge holding on to that, a large negative charge on your halogen, holding on to that positively charged hydrogen ion, it's going to hold on to it more strongly than if you had a weakly negative ion or a weakly negative halogen holding on to the hydrogen. So therefore, as you go down and the electronegativity of the halogen weakens, the bond enthalpy, which is a measure of the bond strength, remember in chapter 8, the bond enthalpy is how much energy it takes to break the bond, is going to get weaker and weaker, as we can see in the table. As we go down the family and our electronegativity of our halogen goes down, the bond enthalpy also goes down. These hydrogen ions are not going to be held as strongly because the halogen they're bonded to is not as negative. Therefore, if we go up here at the top where we have a really high bond enthalpy here for the HF, because fluorine is so strongly negative, because it is so electronegative, it is going to hold on to that positive hydrogen very strongly, and that's going to cause it to be a weak acid. It's not going to want to let go of that positive hydrogen. So that's why it doesn't become a strong acid. It doesn't let go of the hydrogen and ionize completely like a strong acid would. Make sense? All right. Oxoacids. So oxoacids are a class of acids that we learned about back in chapter 2 when we were first naming acids as acids that are made by polyatomic oxoanions, or anions that have a certain number of oxygen atoms around a central atom that could be sulfur, phosphorus, carbon, some sort of central atom that is not oxygen, surrounded by a certain number of oxygen atoms. If you add hydrogen onto it, then you end up with an acid. So we have carbonic acid based on the carbonate ion, nitrous acid based on the nitrite ion, nitric acid based on the nitrate ion, nitrate ion, phosphorus acid, phosphoric acid, sulfuric acid. All of these are based off of oxoanions. And these images are also on the bottom of page 753, some common ones. So comparing their strength, then, we're going to further divide these as whether or not the central atom here we've got carbon, nitrogen, phosphorus, etc. Oh, here we go. So first of all, we're going to have ones where the central atom is in the same, if we're going to make a comparison, the central atom is in the same family. So for example, if we're going to compare bromic acid to chloric acid here, bromine and chlorine are on the same family here. So chlorine versus bromine, which one is going to be more electronegative? Chlorine is going to be more electronegative. So if chlorine is more electronegative, that means it's pulling electrons to itself more strongly. Now, it's pulling those electrons not from the hydrogen, actually, but from the oxygens. So if it's pulling the electrons from the oxygens, these oxygens are not going to be quite as negative, which means that their hold on the hydrogen, therefore, will be weaker. If their hold on the hydrogen is weaker, what's going to happen to the acid strength? Go up or down? Going to be stronger, good. The weaker your hold on the hydrogen ions, the stronger the acid, because acid strength is defined as releasing those hydrogens. So between the two of these, which one would be the stronger acid, chloric acid or bromic acid?
You said which one's going to be stronger?
Yes, chloric acid or bromic acid. Chloric acid would be the stronger of these acids. So if you're looking at the same family for the central atom, the more electronegative that central atom, the more electronegative that central atom, the stronger the acid, because it's going to pull electrons away from its oxygens, leaving them less negative and have a weaker hold on their oxygen, or hydrogen. Yeah, the weaker the bond with hydrogen.
What's the last step?
Stronger acid. Yes, good. The weaker the bond on the hydrogen, the stronger the acid, because the more easily it's going to give up that hydrogen. So that's if you have a different central atom. Now, what if the central atom is the same element, but we're just differing the number of oxygens? So this is going between chlorate, chlorite, hypochlorite, perchloric acid, all of these, just changing the number of oxygen atoms here. So when we're looking at the same central atom, we're just changing the number of oxygen atoms. The rule is that the acid strength, the stronger acids, are those with more oxygens around the central atom. So for example here, if I'm looking at hypochlorous versus chlorous versus chloric versus perchloric, perchloric has the most oxygens around its central atom. It is going to be the strongest acid in this group. Whereas hypochlorous has the fewest oxygens around its central atom. It is going to be the weakest oxygen or weakest acid in this group. So perchloric has 4 oxygens around it, versus hypochlorous has only 1 oxygen around the central atom. The more oxygens around your central atom, if your central atom is the same, so we're comparing the central atoms the same, all of these have the central atom of chlorine, then you can go by the number of oxygens. More oxygens equals stronger acid. Because the more oxygens there that are kind of like the bigger the structure, the less strongly it's going to hold on to its hydrogen atom. There's just more stuff going on there. And it's also going to be more stable. All right, let's try out these rules. Predict the relative strengths of the oxo acids in each of the following groups. So the first one we're comparing is HClO, HBrO, and HIO. So I'm comparing not the number of oxygens, but what here? The central atom. So I've got chlorine versus bromine versus iodide. So if you're comparing the different central atoms, and all these are in the same family, you're going off of electronegativity. Chlorine, bromine, and iodide, which one of those is the most electronegative? Chlorine, good. Which one's the least electronegative? Iodine, good. Electronegativity increases as you go up a family, so chlorine is the most electronegative and iodine is the least electronegative. So which one would be the strongest acid? The chlorine, good. The stronger the electronegativity, the stronger the acid, because it's pulling electrons away from the oxygens. Therefore, the oxygens aren't going to be able to hold on to the hydrogen as strongly. So of these, in this group, HClO would be the strongest acid. HBrO is already in the right order. Well, it's depending on which direction you put the carets. And then HIO would be the weakest acid in that group. Next one, we're comparing HNO3 versus HNO2. Now we have the same central atom, so we're comparing what?
How many
Good. Good. How many oxygens? So what's the rule? More oxygens equals what acid? Stronger acid. So which one would be stronger? Good. HNO3, which is nitric acid, is stronger than HNO2, which is nitrous acid. Questions about these ones before we go on to the carboxylic acids? All right, so carboxylic acid is one of the functional groups that we learned about very, very briefly in Chapter 2. I didn't put too much emphasis on it back then because it's dealt with more in organic chemistry, and this was what we used to change the structure of an organic molecule, is these functional groups. So the carboxylic acid group is the group that is highlighted there. It is a COOH group. It's usually written in the formula as COOH on the end with some R group in front of here. So the most common example of the carboxylic acid that we've been dealing with is acetic acid. So acetic acid back in Chapter 2 was based on the acetate ion. The acetate ion is C2H3O2 minus. So back in Chapter 2, we just stuck a hydrogen on the front of it and called it a day. And said, okay, that's acetic acid because it's the acid form of acetate. Then in this chapter, we started writing it instead as CH3COOH. People are like, why on earth are we writing it this way instead? If you count up the number of carbons, hydrogens, and oxygens, it is still the exact same molecule. And I just said we're just writing it in terms of its structure rather than in terms of here's a polyatomic ion, here's a hydrogen. And the reason for this being is that COOH is the way we write a carboxylic acid group, because here we have on the end carbon, oxygen, oxygen, hydrogen on the end of this molecule. The part in front, our R group, can vary in size and structure. Now, in order for this to become an acid, it has to release, or to act as an acid, it has to release the hydrogen. Now, it releases the hydrogen on the end, not any hydrogens inside of the R group. Any hydrogens inside the R group are off limits. Those are not our protons. Our protons are the ones on the end of the carboxylic acid group. So in this structure, this hydrogen right here is our acidic proton. That's what's going to get donated. Once it gets donated, then we're left with an ion with a negative charge. This is a resonance structure, meaning the negative charge can switch between the two oxygens just by moving that double bond. So resonance structure we learned about very briefly back in Chapter 9. So the strength of these, now all of these carboxylic acids are all going to be weak acids, so we're going to compare their strength by how big R is, Ra. The strength of this acid is going to be dependent on what is R. What is the R group? So let's look at acetic acid versus chloroacetic acid. Very, very similar sizes of R groups. The only difference is chloroacetic acid, one of those hydrogens has been replaced with a chlorine. It's the big difference between chlorine and hydrogen that might affect this. Chlorine is significantly more what than hydrogen? Good, electronegative. It's significantly more electronegative, meaning it pulls electrons towards itself. So just as we learned in the very beginning of this section, if you've got something that's more electronegative, pulling electrons more closely to itself, then its surrounding atoms, in this case usually it's the oxygens, will be less negative because they're losing their electrons, which means what about how strongly they can hold on to their hydrogen? Less strongly. So if they can hold on to their hydrogen less strongly, what happens to the strength of the acid? Get stronger or weaker? Stronger. And sure enough, if you look at the K values, the acetic acid has a 10 to the negative fifth K, while chloroacetic acid is 10 to the negative 3, or 10 times or 100 times stronger of an acid. because this electronegative chlorine pulls electrons towards itself, leaving these things less negative, and if they're less negative, they're going to have less of a pull on that positive hydrogen. So that bond here is going to get weaker and more easily break, meaning it's going to be a stronger acid. It's going to give up that hydrogen stronger. Any questions about carboxylic acids, how they give up their hydrogens? So on this one, I've got a hydrogen. Hydrogen doesn't really pull electrons towards itself. It's not electronegative. Here, chlorine, because it pulls electrons towards itself, all the electrons are going in that direction. So if electrons are going in that direction, these things are going to be more positive. More positive. If they're more positive, they're not going to have a very strong hold on this hydrogen, which is positive. Whereas here, that's not pulling electrons towards itself, so these things are free to be more negative, which means they're going to have a stronger hold on this positive hydrogen, which means they're less likely to give it up, and the equilibrium constant is going to be smaller. Yeah. All right. Let's talk about salt solutions. This is, got one more section after that, but that's just the Lewis definition of an acid base. So if we don't get to that today, that's not so bad. All right. So salt solutions can be acidic, basic, or neutral, depending on what it is the conjugate of. So if you consider a salt solution of sodium fluoride, now this is one of your makeup assignments, so if we don't get all the way through, it's going to be one of the makeup assignments, so you can just watch the videos that I posted for you guys. So sodium fluoride is a salt. It's an ionic compound. It is soluble. What do we use sodium fluoride for? Where might you encounter sodium fluoride? Toothpaste. Good. It's in toothpaste. You go to the dentist's office, they give you a fluoride treatment. It's probably less likely once you're an adult, but certainly for children. Sodium fluoride is used in toothpaste that say contain fluorine, or fluoride rinses, or the stuff that they paint on your teeth at the dentist office when you're a kid to strengthen your enamel. It's a salt. So it's got, in water, it has two different components. It's got the sodium component, Na+, and it's got the fluoride component, minus. In salt solutions, we must consider both of those components as possibly affecting the pH. We learned last time about whether or not conjugates were going to be strong conjugates or weak conjugates. And here was the rule, just to recap. The conjugate acid of a weak base is a strong conjugate acid. The conjugate of a strong base is a weak conjugate acid. So, sodium ion. What base is made out of sodium ion? NaOH. Good. Sodium hydroxide is made from the sodium ion. I know I can't make an acid out of it because making an acid means I add an H+. Would H+ want to go near Na+? No, because they're both positive. So I'm making a base. NaOH, strong acid or strong base or weak base? Strong base. This is a strong base, which means that sodium ion is a what conjugate acid? Weak. So we define weak conjugates as things that are so weak that they have what effect on the pH? None. So weak equals no effect on pH. Now, yeah, weak conjugate acid. No effect on pH. So when we're considering how sodium fluoride is going to affect pH, we're going to ignore the sodium, because that is the conjugate of a strong base, therefore it cannot have any effect on the pH. Fluoride, on the other hand, that is the conjugate of not a base, because you wouldn't want to put hydroxide on it. OH- isn't going to want to go near that because they're both negative. But would H+ want to go on to a fluoride minus? Sure, and what do we make when we do that? HF. HF is an acid. Is it a weak acid or a strong acid? Weak. It's a weak acid, which means that fluoride is a what conjugate base? Good. Strong conjugate base.
Okay, so you said when what is weak, it has no effect on the pH?
If you are a weak conjugate, you have no effect on the pH. Whether you're a weak conjugate acid or weak conjugate base, weak conjugates don't affect the pH at all. Strong conjugates affect the pH. And again, this term strong is relative. This does not mean that fluoride is on the same par as sodium hydroxide. It is not a strong base. It is a strong conjugate base, which just means it is strong enough to affect the pH. Now, the way it affects the pH is by an equilibrium with water. Now, if you look at this reaction I have here, I have fluoride reacting with water at equilibrium arrows, with hydrofluoric acid and hydroxide. So, by definition, a base is a proton acceptor, so it is going to accept a hydrogen from the water. When it accepts a hydrogen from the water, it becomes HF, and the water becomes OH minus. Because we have produced hydroxide, that is what affects the pH. Because pH is shifted when you mix with the balance of hydrogen or hydronium, H3O plus, and hydroxide, OH minus. That's what affects the pH. Now, we have an equilibrium reaction. So what do you think we're going to do next? Ice table, because if we do an ice table and find the concentration of hydroxide, can we find pH from that? Yes, so finding the pH of the salt solutions are just ice tables again. More ice tables. Don't worry, we'll also have more ice tables in chapter 17. You'll get really good at ice tables by the time we're done with this. So, in general, if you have an anion, a negative ion, that is the conjugate of a weak acid, such as the fluoride is a conjugate of HF, which is weak, then it is going to affect the pH, and you're going to end up with a basic salt, meaning the salt is going to end up going pH higher than 7. It's going to be a base. So other examples here, the acetate ion, the nitrite ion, the sulfite ion, and the hydrogen carbonate ion. Let's look at nitrite real quick. Nitrate is NO3 minus. That is not going to make a basic solution. Why not? Why would nitrite make a basic salt solution, but nitrate not make a basic salt solution? What's the big difference here? Yeah, well, sulfite has 3 oxygens, so what's the big difference? Sulfite affected it. No, it goes back to this rule we just talked about here. Strong and weak, weak and strong. Nitrite is the conjugate base of what acid? How do I make this into an acid? Add an H. HNO2 versus how do I make this one into an acid? What's the big difference between HNO2 and HNO3? Good. HNO3 is a strong acid. That's one of the 7 strong acids. Versus HNO2 is a weak acid. Because HNO2 is a weak acid, NO2 is a strong conjugate base. HNO3 is a strong acid, therefore NO3 is a what conjugate base? Weak conjugate base. So that's why it does not affect the pH.
So if it's a strong, so there's a strong conjugate base or acid, that means it's going to be a basic salt solution.
If it's a strong conjugate base, it's going to be a basic salt solution. If it contains a strong conjugate base. In other words, if you have a negative ion that is the conjugate of a weak acid, then you will have a basic salt solution.
Wait, so weak acid is a strong conjugate base?
Yes. Weak acids make strong conjugate bases. So that's it. We'll deal with this one first, and then we'll look at what if it's a strong or a conjugate of a base. All right. So how is this going to affect it? Let's look at this. Calculate the pH of a 0.1 molar solution of that sodium fluoride. Again, do we care about the sodium? No, because it's the conjugate of a strong base, therefore it's a weak conjugate acid. We don't care about it, doesn't affect the pH. We're just worried about the fluoride. So if we're just worried about the fluoride, our equilibrium reaction is going to look like this. Fluoride, F minus, plus water makes HF and OH. Now, this is acting as a base, so it is going to have a Kb. You are not going to find fluoride minus on a table of conjugate base or of table of weak bases anywhere. So we can't look up its Kb value, but we can determine its Kb value from the Ka of HF. So in the last class, we learned that when you have conjugate acid-base pairs, the Ka and Kb value can be related using the Kw of water, where the Kb value would be Kw divided by the Ka of its conjugate acid. So that's what we did at the very end of the last class. Kw is always 1.0 times 10 to the negative 14. Ka, so this right here, 7.1 times 10 to the negative 4th, that is the Ka of HF. Where could we find that? The table. Good. The table of weak acids from a couple of sections ago. So from that, even though we can't just look up the Kb value for fluoride, we can calculate it from its conjugate acid. In this case was HF. Likewise, if I had an acetate ion, I could just look up the Ka value of acetic acid and take 1.0 times 10 to the negative 14 divided by it to find what my Kb value is. So that's the only thing that is new about this section. From then on, it's just an ice table. The only thing new is where did your Kb value came from. It didn't come from a table. You had to calculate it by Kw divided by it. Then we make a nice table. So we already had the ice table up here. 0.1, 0, 0, minus x, minus x, minus x. Equilibrium concentration, 0.10 minus x, x and x. Set that equal to my Kb value and solve for x. So in the interest of time today, we'll go ahead and show you. Solve for x, assume x is small. For all of these, you're probably going to be able to get away with the assumption that x is small. Conjugate acids and bases are going to have small k's. They have small k's. Assuming x is small is almost always a good assumption. So we assume x is small, so we can make the assumption that we can ignore this guy, make our math a whole lot easier. Once we find x, plug, in this case we found x to be 1.2 times 10 to the negative 6 molar. If we plug that back into our ice table, that is the concentration of hydroxide. So to find the pH of that, negative log of hydroxide is POH. So negative log of the hydroxide ion is the POH. Now, because this number is so small, we're adding it to 1.0 times 10 to the negative 7th. Why are we adding it to that number? The reason for this is the concentration of hydroxide in water. In water is 1.0 times 10 to the negative 7th. So at the start of this reaction, we had water. So at the start of it, we had that 1.0 times 10 to the negative molar water. That was from several sections ago when we very first talked about the autoionization of water. So when we're dealing with really, really small concentrations, we're going to add that in. In all of the previous problems, we did not bother because our concentration was so big that adding 1.0 times 10 to the negative 7th is negligible. But because our number is so small here, that's why we added it back in, because it was big enough to make a difference. So add that back in, get our POH, subtract that from 14 to find pH. Make sure your answer makes sense. Fluoride is a strong conjugate base, so we expect it to be a basic solution, meaning its pH should be greater than 7. Again, it's not a strong base, so not hugely greater than 7, but somewhat greater than 7. 8.05 makes sense. It's basic, but it's not hugely basic, just slightly basic. So the pH of our 0.1 molar solution of sodium fluoride is 8.05. We could have done the exact same thing for sodium acetate or sodium hydrogen carbonate, also known as baking soda. So this explains why baking soda is slightly basic, why it bubbles so much when you put an acid like vinegar in it. Because sodium hydrogen carbonate contains hydrogen carbonate, which is a weak acid. Therefore, contains hydrogen carbonate, which is the conjugate of the weak acid, carbonic acid. All right. So you can do the exact same thing with a strong conjugate acid. So this is a little bit trickier because it might be a little bit trickier to recognize something as the conjugate of a weak base. Most of the weak bases that we've been dealing with always were weak bases because what group was on the end of them? NH. So an amine group, some sort of NH group. So the most common of that being just NH3 ammonia. So to make that into a conjugate acid of a base, we're going to add a hydrogen. So the conjugate base of ammonia, NH3, sorry, this is a weak base. What is its conjugate acid? What is the conjugate acid of ammonia, NH3? Am I going to add a hydrogen or remove a hydrogen? Add a hydrogen. So if I add a hydrogen to NH3, I become NH4. Do I have a charge? Plus. Good. Ammonium. So because ammonia is a weak base, ammonium is a strong conjugate acid. So if I had ammonium chloride, do I care about chloride or not in this equation? No. Why not? Chloride is the conjugate of what acid? If fluoride was the conjugate of hydrofluoric acid, what is chloride the conjugate of? Hydrochloric acid. What's the formula for hydrochloric acid? HCl. HCl, strong acid or weak acid? Strong acid. That's a strong acid. Therefore, Cl minus is a what conjugate base? Weak conjugate base. Can it affect the pH then? No. Weak conjugate bases cannot affect the pH, which means we are going to ignore him. Now the question is, can ammonium affect the pH? Yes, because ammonium is the conjugate of ammonia. Ammonia is a weak base, therefore ammonium is a strong conjugate acid. Acting as an acid means it donates its proton. So when I put it in with water, it will donate a hydrogen to the water, leaving us with ammonia and hydronium. If I want to find the pH of this thing, what do I need to do? Ice table again. Ice table again. So this sample problem is on page 758. Calculate the pH of a 0.1 molar solution of ammonium chloride. Same thing. Just another ice table. They're all starting to look the same by this point, right? Again, I'm not going to find the Ka value of ammonium on a table of weak acids. It's just not going to be there. So how do I find what Ka is? How did I find the K in the last problem? Good. Find the K of the conjugate. So the conjugate of ammonium is ammonia. Can I find the Ka value of ammonia in a table? Sure, that's a weak base. If I look at the table of weak bases, I find that it has a Ka value of 1.8 times 10 to the negative fifth. To find the K of a conjugate, it's just Kw, that 1.0 times 10 to the negative 14 divided by it. So we get a value of 5.6 times 10 to the negative 10 for our Ka value. Make a nice table, plug in our Ka value, and solve for x. Same as before. Now once we do that, we'll get our x value. X now is hydronium, so pH is just the negative log of that. You don't have to subtract from 14 like we did in the last problem. So we've talked about acidic salt solutions, basic salt solutions. What was the third kind of salt solution we could have? Neutral. So a neutral salt solution is one in which neither the anion nor the cation can affect the, that's just description, neutral salt solution. Neither the cation nor the anion can affect the pH. So all strong bases are hydroxides of group 1A or 2A. So to be a neutral salt solution, your cation, the positive ion, must be a group 1A or 2A metal. So sodium, lithium, barium, etc. All of those. The exception is beryllium because, as we learned last semester, beryllium is kind of weird because it's a metal, but it can kind of covalently bond. So we're just ignore him. So therefore, we know, just like we saw with the sodium fluoride, sodium is a group 1A metal. 1A and 2A metals are not going to affect the pH of a solution. So that takes care of our cation. What about the anion? Anions that are the conjugates of our strong acids also don't affect the pH, like we saw with the chloride in the last problem. So if you are a salt solution made up of a group 1A or 2A metal combined with a anion that came from one of those 7 strong acids, then you are going to end up being a neutral solution. So for example, sodium chloride is our classic example of a neutral salt. It's neutral because sodium is a group 1A metal. Therefore, it's the conjugate of a strong base. Therefore, it's a weak conjugate acid. Chloride is the conjugate of hydrochloric acid. Hydrochloric acid is a strong acid. Therefore, chloride is a weak conjugate base. Neither one of these can affect the pH. If neither one of these can affect the pH, in the end, we'll end up with a neutral solution. To make another one, we can just do any other combination of a group 1A or 2A metal and the conjugate of one of our strong acids. So for example, potassium is a group 1A metal. It would not affect the pH. If I paired it with, say, NO3, nitrate is the conjugate of nitric acid. Nitric acid is one of our 7 strong acids. That would give me a neutral solution because neither one of them could affect the pH. So summarize all this into a nice little table. This table on the bottom, page 759. So if you have a cation that is the conjugate of the conjugate acid of a weak base, so for example, ammonium, then you have either a small highly charged metal ion or other than group 1A or 2A, so something like aluminum, chromium, iron, bismuth. These are small ions. They don't form strong bases, but they can accept a hydrogen. So they are technically weak bases. Or, notice all of these are some NH group, or N in an NH group. So to make those into their original conjugate, their original bases, you just take away a hydrogen. So ammonium came from ammonia. Methylamine, ethylamine, we're just taking away a hydrogen. That should be a 2. Sloppy there. Sorry. Those are all things that we recognize as weak bases because they end with an amine group. So therefore, because they come from weak bases, they contain strong conjugate acids, and you will end up with an acidic solution. To make a basic solution, the conjugate base of a weak acid. So Cn- comes from hydrocyanic acid, which is a weak acid. NO2, nitrite, comes from nitrous acid, a weak acid. HC3COO-, that's the acetate ion, came from acetic acid, which is a weak acid. So those things all are the strong conjugate bases of weak acids, so they will make basic solution. Cations that do not affect the pH, those are our group 1A or 2A metals, so lithium, sodium, barium, etc. Anions that do not affect the pH of a solution are the conjugate base of a strong acid. So HCl came from HCl, which is a strong acid. NO, that should be an O, not a 0. NO3 came from HNO3, nitric acid, etc. We're just making these from strong acids. So none of these things will affect the pH. So let's real quick predict a few things, and then we'll be done for the day. Predict whether a 0.1 molar solution of each of the following solutions will be acidic, basic, or neutral. So for the first one, we have lithium iodide. Can lithium affect the pH? No. Can iodide affect the pH? No. Iodide is the conjugate base of a strong acid. Hydroiodic acid is a strong acid. So can that affect the pH? No. So what kind of solution? Acidic, basic, or neutral? Neutral. Ammonium nitrate. Which one will affect the pH, the ammonium or the nitrate? Ammonium will affect the pH. Why will nitrate not affect the pH? Good, it's the conjugate of a strong acid, nitric acid. So ammonium is the conjugate of a weak base, so it will affect the pH. So is this solution going to be basic or acidic? Acidic, good, because that is a strong conjugate acid. So this will be acidic. It is in this category. Where am I? Right here. It is a conjugate acid of a weak base, therefore I can make an acidic solution. Strontium nitrate. We already said nitrate's not going to affect the pH. Can strontium affect the pH? No. Why? Good. Group 2A. So what kind of solution is this one? Neutral. Potassium nitrite. Can potassium affect the pH? Nope. Group 1A. Can nitrite affect the pH? Yes. Nitrite is the conjugate of nitrous acid, which is a weak acid right there. Therefore, we make a basic solution. Sodium cyanide. Can sodium affect the pH? No. Can cyanide affect the pH? Yes. Cyanide is the conjugate of a weak acid, therefore it is a basic solution. Now, if you had a combination of both, say I had ammonium cyanide. Ammonium can affect the pH and so can cyanide. At that point, I would not ask you straight up, is this going to be acidic or basic? Because it depends on the relative K values. Whichever one has the larger K value, the ammonium or the cyanide, that's the one that's going to have the bigger effect on the pH. I wouldn't ask you that question, but I can't guarantee you won't see it on Learn Smart. Because again, it's tricky. All right. I think that was, yeah. Right there. The bigger K value has when both of them.